All right, we continue. I've thought it through and decided perhaps what is the best way I can illustrate it. Maybe the problem is a little bit more it's not complex, but it's a little bit more non-standard than I would want it to do on a second example, but I figured that instead of removing it, I'll follow through, right? This is a video, you can always watch it over and over and see, so hopefully we'll get something out of it. So, starting again, we have a frame here, which is doubly fixed and has a hinge here in the middle. The structure we concluded is indeterminate to the second degree, and we know that the loading in this case is a settlement of support at A, capital A, of 1 inch. I don't know why I have an A hat, just A, with is 1 inch downward and 2 inches to the left. That's what happens at A. So because it's indeterminate to the second degree, we have to take two redundants, and there are choices, right? And in this particular case, I am going to choose first the redundants to be the horizontal reaction and the vertical reaction at A. So what is it that remains? That's what was a little bit awkward to draw because it's not something that you normally find. But what we need is something that cannot take, that without these redundants can move vertically, can move horizontally, but cannot rotate. So some sort of idealization would be like this, right? You imagine some sort of a balls, right? And a rigid angle, and like a roller blade, right? And these are also here. So this rigid structure, these rigid angles can rotate, can move this way. I'm sorry, not can move this way. This thing can move down on it and roll over there, right? And if it needs to move to the right, it can, because this top thing can roll on the balls, right? So this angle can roll left or right, right? This angle can move left and right, and that allows this wall, I mean this element, to move to the left and to the right, and it can actually, the the left column can move up or down because it can roll on this thing, right? Okay, that's as good as I can draw it, and that's it, right? So you have your redundants x1 and x2, this is your supports. Now you immediately see what? That this is a situation in which we've chosen the redundants and they coincide with the movements. So looking back at what I wrote earlier in this video, this is the case, and we are looking at the flexibility matrix times the redundants plus 0, because there is no delta, equals to delta, right? So this is the problem that we would solve in this particular case. This delta is directly known in this particular case because why? When these are the final movements at the locations of the redundants, therefore in the horizontal direction, what is the movement? 2 inches to the left. So if I choose that as the first one, I would say there is 2 inches negative because it's against the direction that I chose the redundant. There is 1 inch downward, so it is -1 because it is against the other redundant, and that's it, right? Those are my two deltas. So I have my values here. I can erase this to make it cleaner if you want. This is like that. So I have my two values here by pure inspection, and all I need to do, of course, is to calculate my flexibility matrix. That's it, right? Get my flexibility matrix. Now, my flexibility matrix, like in every problem that is 2 by 2, is just F11, F12, F21, F22, right? And that is sketch 1 times sketch 1, sketch 1 times sketch 2, sketch 2 times sketch 2. So what we need is the sketch x1 equal to 1 and the sketch x2 equal to 1. So let's follow the logic there just so that you can practice your statics, right? So I'm going to do the x1 equal to 1, then I'll erase it, we'll do the x2 equal to 1. So here is the structure. It has no x2 now, right? like that. No x2, but it has an x1 equal to 1. And because of this angle, remember, this has the ability to take moment, right? So we can't have a moment there due to this constraint. We don't know what it is, it's going to be determined by statics. We don't have an x2, this is the x1 equal to 1 case. This other side is fixed. So this, if you'd like, it's a reaction there at that point, right? Call it M, capital MA if you want. So now we have to do the statics on that. Okay? And we can, because how many unknowns do we have? 3 and 1 is 4, but we have one hinge here, so that's going to be no problem, right? So first, my free body diagram that cuts through the hinge, it's like this and like this, right? And here we have some moment that I don't know what it is, plus a 1 here. Here there is no moment because that's the hinge. Summing forces in the horizontal direction, this is a 1. Summing forces in the vertical direction, hey, there can be no vertical here, there can be no vertical here either, right? So that is 0. And now, summing moments about this point, we have, actually let me choose it the other way so we get positive. So, now we have 1 times what? 1 times b, right? Because this distance is b. So summing moments about here, minus 1 times b plus ma equal to 0. So we get that ma is equal to b, right? So if I came here, I can just say that that's actually happens to be b. Now that we know that, I can also go from the hinge to the other side, right? The hinge to here. So going from the hinge to the right, it would look like this. We found that there is a 1 going inward, no vertical, and so that's it, right? And over here there are 3 reactions. So summing horizontals, this is a 1. Summing verticals, the vertical is 0. And summing moments clockwise gives me a counterclockwise here of 2b, right? And so we find that at this support, the reactions are 2b, 1 this way, nothing vertical. Okay? Now, I will erase over here to give us a little space. And to realize this is the x1 equal to 1 sketch. So that's it, right? I mean, at this point now you guys know how to do your bubbles and to write your equations. So let's do that, for example, here, right? So if we take this bubble here, what would we find? We would find a free body like that. We have to generate some coordinate, right? So let's call this coordinate y. Then this would be a 1 to the left, a moment b this way, a height of this chunk that I cut being y, and at this point where we cut, we have, well, I have to decide which my sign convention is, so it doesn't matter. I'm going to take, let's say, compression on the outside to be positive. So I'm going to take this to be my M1, so I don't have to think about it. I'm going to use compression on the outside. So I'm going to get then minus M1, and there is of course a shear here. And there could be an axial, but I don't really care because I'm going to sum moments about here. I'm going to get minus M1 plus B minus Y equal to 0, from where M1 is equal to B minus Y, right? So we can come here with our 1 here, and we know that in this bar M1 is equal to B minus Y. Okay? Now, actually, it would have been so much easier if I didn't erase it, because now I want the moments on this part. And clearly, I can, and I guess I will, because I erased it. So if I take this bubble, Otherwise I would have started at the hinge and come to the left, right? But if I take that bubble, I have this and this, right? There is a moment here, B, and there is a load here of 1. The height from here to here is B, right? And here where I cut, I said I'm going to take compression on the top to be positive, so that's my shear and axial. And if I saw moments about there, I'm going to say minus M1 plus B minus B is equal to 0, and therefore I'm going to find that M1 is 0. Okay? So, go like this, and I see that my moment M1 here is 0. I confirm that in my moment equation for this bar, which was, which was B minus Y, when Y is equal to B, gives me 0, so that's fine. The presence of the hinge makes no difference, right? Because there's no load applied there. I can keep going like this. So this works all throughout that bar, right? And I can find the moments on this other one by taking the bubble here and looking at the free body diagram of that, and taking a free body diagram of that, we would have something like this, right? First I need to get a coordinate starting here. Let me call it Z. So that would be a 1 to the left, a moment of 2B, a height of Z, and at the cut I would have a shear, perhaps an axial, although there's 0 in this case. And I said I'm going to use moments that give compression on the outside, so that would be my M1. Then I would say minus M1, no, plus M1, plug, minus 2B against plus 1 times Z is equal to 0, therefore M1 is equal to 2B minus Z, right? So our moments on this bar is M1 equals 2B minus Z. Now let's check, right? 2B minus Z, Z can be as large as 2B, so by the time we get here it'll be 0 and it'll be compatible with this. So this is my x1 equal to 1 sketch, right? And I can certainly do my x2 equal to 1 sketch, and that would present no problem, and that's it, right? So let's imagine that you've done it, and so you have your thing here like this, and this is your x2 equal to 1 sketch. Excuse me, let me close here. So you have your x1 equal to 1, which I did complete. You have your x2 equal to 1 that I will not do. And then what would you do? Sketch 1 times sketch 1, right? And gives you F11. Sketch 2 times sketch 2 gives you F22. Sketch 1 times sketch 2 gives you F12, which is equal to F21. And the problem would be F11, F12, F21, F22 times the two redundants, x1 and x2, equals delta, which in this case is minus 2 and minus 1, right? Solve that, and now you have x1 and x2. And what would be the final moment diagram, final shear, final everything? It's just this sketch times whatever value of x1 comes out, plus this sketch times whatever value of x2 comes out. This plus this is the answer, right? Since there is no P sketch in the case of settlements, right? And that's it. So we've solved the problem in the case where you've chosen the redundants to be coincident with the settlement. Now let's conclude by looking at the case where we choose the redundants non-coincident. So in this case, we have this side, we leave it alone. And now we're going to choose this side, right? Now I'm going to choose, how many redundants do I need on the right side, on B? 2, right? Why go through the complicated thing with the angle and so on? Let's just choose the horizontal and the moment, right? That is, we put this on a roller, and then we have x1 and x2 to be those, right? We remove the horizontal capacity at this point, this redundant x1, and we remove the moment, becomes a pin, a roller, x2. So that's x1 and x2. Again, for x1 and x2 equal to 1 and x2 equal to 1, we can calculate the x1 equal to 1 diagram and the x2 equal to 1 diagram, right? And I guess in this case I'm going to need it to do the computation, but let me just say that in this instance the redundants do not coincide with the settlements, so we are looking at a problem that says flexibility matrix times redundance plus delta equals 0, right? Because there is no movement here. The movement is elsewhere, right? So the effect is going to reflect it here. Flexibility, it can be computed in the regular way, right? x1 equal to 1, get the sketch. x2 equal to 1, get the sketch. Do the stuff, you got that. The question then is, how do we get delta 1, delta 2? What are delta 1 and delta 2? Physically, delta 1 and delta 2 are how much this point moves to the right, or how much does it move horizontally, I should say, and how much does this column at this point, its tangent, which is vertical, tilts when point A suffers these movements. Okay? 1 inch downward and 2 inches to the left. For that, at this point, we have to forget about the problem of statically indeterminacy and all of that stuff. We just need to calculate what is the movement. So it's like this, right? What is the movement at this point in the horizontal and in the rotations due to something here? So we are looking at the situation where we say 1 times delta plus R transpose S is equal to 0. That's how we calculate our movements, right? We always calculate our movements away from where we apply these things by, well, actually I shouldn't say away. We always calculate our movements like this. 1 times delta times R transpose S equal to 0, right? So first I want to calculate delta 1. Let's say I focus on getting delta 1. So this is my x1 equal to 1. So I put my 1 kip load there, and we have to do statics, right? So how are we going to do statics quickly? From the hinge downward, I see a 1. That means that this gives me a 1 to the left, right? This is going to rotate like that, counterclockwise. So this has to be downward. That's 2b, and this is a. So it looks like that's 2b over a. Correct? Looks like that's 2b over a. I think that's right. Therefore, there needs to be a shear, which is 2b over a here. And then that means that the other free body on the other side is like this, with a 1 to the right and a 2b over a coming down, which requires that over here there be 2b over a going up, that there be a 1 to the left. And there's going to be a moment, right? And this moment here, let's say, if we call it M, is going to be M, summing moments about here, M, plus 2b over a times a, plus 1 times b, right, equal to 0. Therefore, M is equal to minus 3b, right? I put the 1 there. Let me double check myself. 1 times 2b divided by a. This is like that. That's like this. This is here like that. 2b over a. 2b over a. 1, 1. 2b over a times a gives me 2b plus b equals 0, that gives me m is equal to minus 3b, right? So that means that this moment here is actually this way, 3b. All right? So I'll put this thing here. The reaction here is 2b over a. The reaction here is 1. The reaction here is 3b. And on this side, the reaction is 2b over a. I'll erase these little gizmos here. And let us focus on our equation, right? This is x1 equal to 1, which is used to calculate delta 1 for settlements that are not at the location of the redundants, right? So we have x1 equal to 1 here. We calculate the reactions. So what is our vector of reactions? It's a vector that lists the reactions due to the 1-kip load in any order you want, as long as you're consistent. So I will start on this side and use normal things like to the right, up, and clockwise. So it will have minus 1, 2b over a, minus 3b, and then over here, that's not a reaction, and this is minus 2b over a. So those are my reactions, right? And what are the settlements? Well, at this point in the horizontal, what is it? 2 inches to the left, right? So minus 2. In the vertical, 1 inch down, so that's a minus 1. Rotations, nothing. And on this other side, was there any vertical movement? No. So those are my settlements and those are my reactions due to x1 equal to 1. Therefore, I can get delta 1 by saying 1 times delta 1 plus R transpose, which is minus 1, 2b over a, minus 3b, minus 2b over a, multiplied times this, which is minus 2, minus 1, 0, and 0, right? So that's this one times that one. So it's 1 times delta 1 plus, I'm going to open a parenthesis, minus 1 times minus 2 is 2. 2b over a times minus 1 minus 2b over a. Minus 3b times 0 minus 2b times 0. So that's it, right? So I find that delta 1 is equal to that on that side. So it's 2b over a minus 2. Okay? So of the vectors that of the two numbers that we need to complete this problem, when we have the flexibility, would be, that's the first one, 2b over a minus 2. Okay? Now to finish what? To finish, let's erase and do the case x2 equal to 1. Right? So now x2 equal to 1. Oh gosh, I forgot which direction I took x2. I'm going to assume it's like this. If I didn't, forgive me. So this is the case x2 equal to 1. Do a counterclockwise moment like that, right? So we need to calculate, of course we needed all our internal moments to calculate the flexibility, but we need the reactions to get delta 2. I'm trying to get this guy now, right? And I know that the answer is going to be R1 transpose times the settlement plus 1 times delta 2 equal to 0. So I go here and I start doing statics again. So take a look at the free body diagram from the hinge to the right. That's going to look like this. There's going to be a moment of 1 here. And so that's counter. So I'm going to need a vertical like that. That's going to be summing moments about here. It's going to be minus 1. And this is 1 times a, right? So it's going to be 1 over a. This one is going to be up 1 over a. Horizontals are 0. And that's the end of the game on that one, right? That's the free body diagram of the left side. There's nothing here and there's nothing here because there's no load applied there. Now we go to the other side, which is like this, and we have our 1 over A, nothing horizontal, right? And we are at hinge, and there are 3 reactions here. Summing forces in Y, that's 1 over A, summing forces in X, that's 0, and summing moments, there is a moment here counterclockwise equal to 1 over A times A, which is a 1, right? So we find that our reactions are 1 over A going up, nothing horizontal, and a moment of 1. At this point, we can then erase these sketches because I'm not doing the flexibility now. And we can say, all right, what are our reactions in the order that we decided? Nothing horizontal, 1 over A vertical, minus 1 for the moment. And on that side, oh my gee, I forgot. I erased it again without knowing. I think it was 1 over A. Let's see. This is a 1. Summing moments about here. Yeah, that was 1 over A down, right? And then this was 1 over A up. So, yeah. So that means in this point, minus 1 over A. So those are the reactions on that structure in the case x2 equal to 1. And the settlements, they don't change. They are the same thing, right? At this support, in the x direction, minus 2. In the y direction, minus 1. In the rotations, nothing. And on this support, nothing. So we have 1 times delta 2 plus R1 transpose S equal to 0. This thing gives me 1 times delta 2 plus 0 times minus 2 is 0. 1 over A times minus 1 is minus 1 over A. Minus 1 times 0 is 0, and this times this is 0. And so we find that delta 2 is equal to 1 over A. Okay? Which is the rotation. So we have succeeded calculating delta 1 and delta 2. Therefore, you could just formulate your flexibility, put this on the other side, solve, done. What is the final moment diagram? Sketch x1 equal to 1 times x1 plus sketch x2 equal to 1 times x2. Add them together. That's the answer, right? So this is an example, quite involved. I was intending to come up with something perhaps simpler for the first time around, but maybe it worked out fine. I asked Ishmael to prepare a little something simple for you to practice with. So, you know, it should be posted maybe even today or at the latest tomorrow for you to practice these settlements. As far as I can think of right now, I believe that this is it regarding coverage of new material. Okay? That is, I haven't done an example with a structure in which what we have is loads. So in the next lecture, I will solve the standard situation, right, where the action that is producing effects is not temperature, is not settlement of supports, is an applied load. Of course, that's perhaps well, I don't know if it's the easiest case, they're all the same, but perhaps the most standard case, right? So we will do that example, but there's really nothing new in it, right? So we are done with as far as the material in the course is concerned. Once I do that example, that's going to cover us, that's going to be, let's say, the class on Wednesday. Then I want to go back and revisit something that we did a little while ago, which is the thing of stress and strain, which I don't think that we did it with sufficient calm. And don't remember why that happened, but I feel that you didn't get a fair presentation of the issue of stress and strain rotation of stresses, passing from stresses to strains, plane stress, plane strain, and so on. So I want to dedicate one lecture to review that and to do some problems, maybe two, I don't know. We have plenty of time, so and then there is also the recitations that I'm sure Ismail is preparing for you. So hopefully we'll be very well prepared by the time that the final comes in. I checked today to see if the date and time had been posted, but as far as I could find in the university, I could not find the date posted, but I assume that very soon we will know. All right? Okay.